There is a bird sitting on the wire above your street right now, and you have never once stopped to look at it. It weighs about as much as a chocolate bar. It appears at a glance to be simply black. Linnaeus named it vulgaris in 1758. Common, ordinary, unremarkable. Linnaeus was wrong, and what follows is the evidence. Because this bird can challenge the foundational assumption of human linguistics, uses pharmaceutical plants in its architecture, and moves in flocks of 1 million without a single collision, obeying the same mathematical laws that govern magnets on the edge of phase transition. Stay with me, because somewhere in the middle of this video, a 3-gram brain is going to take on Noam Chomsky. And at the end, the story of 100 birds that became 200 million. Pick up a pair of binoculars and point them at a starling. What you thought was a blackbird becomes something else entirely. A team of researchers at the University of Groningen published a study in 2021 on the nanostructure of starling feathers, and what they found reads like materials science more than ornithology. Inside each feather sit melanosomes, microscopic organelles packed with melanin pigment, arranged in a single layer beneath a film of keratin so thin that its thickness alone determines the color you perceive. Change the angle of the light, and the bird shifts from violet to emerald to bronze to ink blue, not because its pigment changes, but because the interference pattern of light waves bouncing off that keratin film changes. This is called structural coloration, the same principle governing soap bubbles and butterfly wings, executed in a living creature that nests in your roof. The beak is an engineering story of a different kind. Most songbirds use their bills as grasping instruments, close, grip, consume. The starling inverts this. It drives its closed bill into the ground, then forces it open underground, spreading the soil apart like a surgeon opening an incision. The muscles responsible for this spreading motion, the protractor muscles, are enlarged in starlings relative to other passerines. The skull is narrow and tapered, which allows the eye to shift forward and peer directly down the length of the open bill into the gap it has created. The bird sees what it is digging toward. Ornithologists call this open bill foraging, and it is the precise adaptation that allows starlings to exploit lawns, pastures, and golf courses, any short-cropped grass beneath which insect larvae and earthworms live invisibly. And because starlings have spent millennia feeding beside large grazing animals, they still land on the backs of cattle and sheep, methodically removing ticks and parasites from their skin, a partnership maintained for thousands of years. But neither the feather nor the beak is what this bird is actually about. The starling's primary weapon is its voice. It ranks among the finest vocal mimics on Earth, in the same category as parrots and mockingbirds, but with a fundamental difference. A parrot learns a set of sounds and reproduces them. A starling composes. Its song is a sustained, structured sequence of whistles, clicks, rattles, and appropriations that can run for a minute or longer. Researchers have identified 4 distinct categories of sound within a single starling song, assembled in a specific order by each male. Into this architecture, the bird weaves sounds borrowed from other species: orioles, thrushes, windchats, raptors. Beyond the natural world, it absorbs car alarms, camera shutters, telephone rings, gate hinges, and dogs barking. One keeper of a captive starling reported that a telephone rang from inside a bush in his garden on a regular basis. The starling was entertaining itself. What makes this more than a circus trick is the mechanism. The starling is what researchers call an open-ended learner. Most songbirds crystallize their repertoire in youth and stop acquiring new material entirely. The starling never stops. The older the male, the richer and more layered his output. Every sound added to the repertoire is a record of a place visited, a season survived. The song of a mature starling is a sonic autobiography, a living archive of lived experience. Females read this archive directly. Research published in Behavioral Ecology and Sociobiology showed that males with more complex repertoires find mates more quickly, because a broad repertoire is a reliable indicator of age and multi-season survival. The female is selecting for demonstrated durability. The proof sounds from every branch in spring. On the 27th of May, 1784, Wolfgang Amadeus Mozart walked into a Viennese pet shop and bought a starling. In his expense book, he wrote, "Starling bird, 34 Kreutzer," and beside it a short musical notation. The melody the bird was singing bore a striking resemblance to the opening theme of the third movement of his piano concerto number 17 in G major, which Mozart had completed only weeks earlier. The bird sang his theme with two modifications: a pause inserted in the wrong place and a G sharp substituted for a G. Mozart noted the bird's version and wrote beside it, "That was beautiful." He kept the starling for 3 years. When it died on June 4th, 1787, he held a garden funeral with a procession, mourners in veiled black, and an epitaph written in verse. Psychology professor Meredith West of Indiana University, who spent years studying starlings, wrote that Mozart's grief, despite the comic register of the poem he composed, was entirely genuine. Starlings form real attachments to people and people to them. West went further. She argued that A Musical Joke, the bizarre, structurally disorganized composition Mozart completed 10 days after the bird's death, is a memorial. For decades, musicologists assumed Mozart was parodying talentless contemporaries. West proposed that the composition is written in the bird's manner, musical ideas scattered without apparent logic, rearranged without resolution. The starling is in the score. A creature weighing as much as a chocolate bar influenced one of the most consequential composers in history. This is not legend, it is documented in Mozart's own handwriting. Did you ever hear a starling sing at close range? Not distant chattering on a rooftop, but from 3 meters away, a full performance. Write it in the comments if you did, especially if it was mimicking something specific: a phone, an alarm, another bird. I am genuinely curious because what those people describe is usually unforgettable. In 2023, a paper led by Jean-Nicolas Audet at Rockefeller University under Eric Jarvis tested 21 species of wild-caught birds on cognitive tasks while simultaneously rating their vocal learning complexity. The result was a clean correlation. Starlings, blue jays, and gray catbirds were both the best vocal learners and the best problem solvers. And these three species had disproportionately large brains relative to body size. Jarvis proposed the term vocal cognitive complex for what he was seeing: complex song acquisition, general cognitive flexibility, and enlarged brain volume evolving together as a single package, the same trajectory, he noted, that characterized human cognitive evolution: complicated speech, problem-solving ability, expanded brain, arriving in parallel. But the event that most severely disturbed the scientific consensus happened earlier, in 2006. Timothy Gentner, a neuropsychologist at UC San Diego, published a paper in Nature that sent a tremor through linguistics. He trained starlings to distinguish between two types of acoustic sequences. The first type used what is called finite state grammar, sounds added to the beginning or end of a chain. This was the grammatical level assumed to describe the entire communicative range of non-human animals. The second type used context-free grammar with recursive center embedding, meaning a sound inserted inside another structure, the grammatical architecture that underlies human language. The architecture that Noam Chomsky argued separates humans from every other species on Earth. 9 of 11 starlings learned to discriminate recursive structures with approximately 90% accuracy. It required 15,000 training trials over roughly a month of work with food reinforcement. 2 birds never acquired the skill, but 9 did. When I first encountered this research, I went back and reread it because the claim is almost too large to accept. A 3-gram brain, recursive grammar, the capacity that linguists spent decades treating as a uniquely human achievement. The necessary caveat exists. Cognitive scientist Timothy Stokes argued in 2007 that the birds were probably not parsing embedded structure the way humans do, but were instead using a simpler counting strategy, tracking the number of elements and matching totals. That interpretation reduces what the starlings demonstrated from full recursive understanding to a very sophisticated form of quantitative abstraction. But even the reduced version means these birds are operating with acoustic abstractions at a level that nothing in the animal cognition literature had predicted. The debate Gentner ignited has not been resolved. What is beyond dispute is that a starling began it. The starling also possesses brain regions functionally analogous to human speech centers. Specialized nuclei in the forebrain connected by neural circuits that resemble the corticobasal pathways found in mammals, and these regions undergo seasonal neuroplasticity. In spring, when song production peaks, they grow. New neurons form, new connections are established. In autumn, when song serves no reproductive function, the volumes contract. The brain of a starling restructures itself twice per year. Nothing in human neurobiology works this way. We cannot seasonally expand and reduce specific brain regions on a calendar. The starling builds its nest in cavities, tree hollows, crevices in walls, ventilation openings, nest boxes. This is not a preference. It is a requirement. The reproductive strategy of the species is entirely organized around this constraint. The male secures a cavity first, cleans it of debris, lays a foundation of dry leaves and bark and moss, and then does something that takes several minutes to understand properly when you first encounter it. He decorates, and in decorating, he becomes a pharmacist. Helga Gwinner of the Max Planck Institute for Ornithology spent years documenting what male starlings specifically select for nest material. The birds actively choose aromatic plants, yarrow, hogweed, elder, parsley, chervil, not random vegetation, not whatever is closest, specific species with high concentrations of volatile chemical compounds. Males display these plants to females before incorporating them into the nest structure, holding them up as if presenting them for inspection. In 2018, Gwinner and Karen Cooper from the University of North Carolina replaced 36 natural starling nests with artificial ones. Half received the aromatic herbs, yarrow, hogweed, parsley, elder, ground elder, and willow. The other half received only dry grass. Egg temperatures in the herb nests were higher. Parents returned to incubate more consistently and allowed eggs to drop below the critical 27-degree threshold, at which embryonic development halts far less frequently. Chicks from herb nests were heavier at fledging and carried lower parasite loads. The critical finding was the mechanism. The herbs were not acting as insulation, they were altering parental behavior. The aromatic compounds appeared to produce a mild sedative effect on the birds, extending incubation bout lengths and advancing the onset of daytime activity. Gwinner noted that several of the plants involved are used in folk medicine and have documented sedative properties. The starlings were using plants not as building materials, but as pharmacological agents, tools for biochemical influence. We have lived beside these birds for thousands of years and never noticed they were running a dispensary. Earlier research had shown that wild carrot and small-flowered hawthorn, two of the plant starlings most consistently select, significantly suppress the development of blood-sucking mites under laboratory conditions. Garlic mustard, which grows everywhere and is accessible to starlings but which they consistently ignore, shows almost no anti-parasitic activity. The birds are not gathering green material indiscriminately, they are selecting the compounds that work. 4 to 6 eggs per clutch, pale blue, unmarked. Incubation lasts 12 days. Both parents sit during daylight hours. The female carries the night shift alone, assisted by a brood patch, a bare skin surface on her abdomen through which heat transfers directly to the shells. Chicks leave the nest at 19 to 22 days, fully fledged and flight capable. Not the helpless naked creatures you associate with other species. Within 3 to 4 days of fledging, they are nutritionally independent. What is less often noted is the synchrony. Within a single starling colony, females begin laying within a few days of each other. Chicks fledge within 1 to 2 days of each other. This is not coincidence. When hundreds of fledglings emerge simultaneously, the probability that any single bird is selected by a predator drops sharply. Predators become overwhelmed by abundance. Starlings solved this optimization problem long before game theory was formalized as a mathematical discipline. A single pair can raise 2 broods per season, producing 8 to 12 offspring annually. That productivity is one reason the species has colonized half the Earth. And now we arrive at what most of you came here to see. In Denmark, they call it sort sol, black sun. Twice yearly, in spring and autumn, the marshes of southwestern Jutland near Tønder and Ribe receive starling flocks of a scale that can occlude the setting sun, up to 1.5 million birds in a single location. They rise at dusk, and for 20 to 30 minutes they paint the sky with shapes that have no name. Spheres, sheets, funnels, ribbons that stretch and contract as if the air itself is breathing. This is murmurations. The word comes from the Latin murmur, a soft, continuous sound, because when a million wings beat simultaneously, you do not hear individual impacts. You hear a bass note. Low, sustained, growing louder, as though someone has plucked a string the width of the horizon. The question the phenomenon raises is this: how does a million birds move without collision, without a conductor, without a plan? In the 1930s, the British ornithologist Edmund Selous proposed that starlings must possess a form of collective telepathy. They must think together simultaneously in a flash of many minds, he wrote. A theory that sounds absurd until you appreciate that Selous had no alternative. No computational tools, no mathematical framework, No other explanation existed. The answer came in 2008. A team of Italian physicists led by Andrea Cavagna and Irina Giardina of the National Research Council's Institute for Complex Systems set up cameras near the National Museum in Rome, where starling flocks perform each evening. They filmed flocks of up to 4,000 birds from multiple synchronized angles and reconstructed their movements in three-dimensional space. Three things emerged. First, there is no leader, not a temporary one, not a rotating one, none whatsoever. This was confirmed statistically. Second, each starling tracks not every nearby bird, not a radius of influence, but exactly 7 individuals, not 6, not 8. The 7 nearest neighbors, regardless of how tightly or loosely the flock is packed. George Young at Princeton confirmed this in 2013, publishing in PLOS Computational Biology. 7 appears to be the number that optimally balances collective cohesion with the energetic cost of individual adjustment. Third, and most unsettling, the behavior of the flock is governed by what physicists call scale-free correlations. When one bird on the edge of the flock changes direction, that information propagates through the entire mass essentially instantaneously, not through a chain reaction, but as a wave that crosses the full cloud with negligible delay. The size of the flock does not matter. The information reaches every member at the same speed. Physicist Giorgio Parisi, who would later receive the Nobel Prize in Physics in 2021, partly for related theoretical work, co-authored the landmark 2010 paper in the Proceedings of the National Academy of Sciences. He wrote that behavioral changes in one animal influence the state of all others in the group, regardless of group size. Scale-free correlations are what physicists observe in systems at the edge of phase transition, water approaching freezing, a ferromagnetic material approaching the Curie temperature, the moment before crystallization. The flock of starlings exists permanently at this edge, not by accident, but because natural selection drove it there. A system at criticality is maximally sensitive to perturbation. Information passes through it without loss. When a peregrine falcon strikes, the response is total and immediate. What happens when the falcon arrives is worth describing in detail. The flock fractures, flows around the predator, reconnects behind it, pulses, elongates into a ribbon, and reassembles into a sphere. The falcon's brain, tuned by evolution to isolate and track a single target, is overwhelmed by too many simultaneous trajectories changing too rapidly. This is called target degradation. The predator cannot fix its attention on any individual because every individual is indistinguishable from the motion of the whole. In Denmark, observers have documented a further countermeasure. Starlings within the flock will bombard a penetrating raptor with droppings and regurgitated matter, coating its feathers with sticky material that degrades flight performance. In rare documented cases, the hawk falls. Have you seen a murmurations in person? Not video. With your own eyes, standing outside, watching it happen above you. Write where and what it felt like, because people who have seen it in person describe it in remarkably similar terms, as something they cannot adequately explain and have never forgotten. Now we arrive at the story that begins as a whimsical anecdote and ends as an ecological case study. March 6th, 1890. Wet snow was falling on New York City. A wealthy pharmacist and amateur ornithologist named Eugene Schieffelin carried cages of 60 European starlings imported from England into Central Park and opened the doors. The following year, he returned with 40 more. The popular account of his motivation, repeated constantly ever since, is that Schieffelin intended to introduce to America every species of bird mentioned in the works of Shakespeare. The starling appears in Henry IV, Part 1, when Hotspur suggests training a starling to speak the name Mortimer repeatedly in the ear of the king as a form of psychological torment. It is a perfect story. It is probably not true. John McNeill, a researcher at Duke University, conducted a thorough archival analysis and found no primary source connecting Schieffelin to a Shakespearean motivation. The first mention of this explanation appears in 1948, 42 years after Schieffelin's death, in a naturalist's book that cited no sources. Schieffelin was serving as chairman of the American Acclimatization Society, an organization dedicated to introducing European species to North America for economic and cultural reasons. Shakespeare was likely not a factor, but the legend has proven more durable than the evidence against it. What is beyond dispute is the outcome. Approximately a third of the released birds survived their first winter, sheltering under the cornices of the American Museum of Natural History on the western edge of the park. By the 1920s, starlings had reached the Mississippi, by the 1940s, the Pacific coast. Today, North America holds approximately 200 million European starlings. 200 million birds descended from 100 in a little over a century. Genetic analysis published in Ecology and Evolution confirms the bottleneck in the DNA. Mitochondrial diversity is low throughout the entire continental population, consistent with a founding event of extreme smallness. Every one of those 200 million birds traces to the flock that sheltered under the museum cornices in the winter of 1890. The reason is the starling's generalism. It eats beetles, flies, grasshoppers, caterpillars, earthworms, snails, spiders, seeds, grain, berries, grapes, cherries, and food waste from bins. It nests in tree hollows, on buildings, inside ventilation systems, under bridges, in lampposts. It begins nesting earlier in the season than most native species, occupying the best available cavities before resident birds return from wintering grounds. It is aggressive in defense of those cavities, evicting eggs and nestlings of other species without hesitation. Woodpeckers, bluebirds, purple martins, great crested flycatchers, all of them lose nesting sites to starlings. The species appears on the IUCN's list of the world's 100 most dangerous invasive species. The annual agricultural damage in North America is estimated at close to $1 billion. 100 birds in a park. 130 years later, 200 million across a continent. But now consider the other side of the world. Since the early 1980s, the starling population of the United Kingdom has declined by more than 80%. 80. In 1980, 5 birds, where today 1 remains. The species was added to the UK Red List, the highest category of conservation concern, in 2002. A bird that was still regarded as a pest in the 1990s became protected within a decade. Between 1995 and 2023, according to the Royal Society for the Protection of Birds, numbers declined by 57%. The 2025 Big Garden Birdwatch, in which hundreds of thousands of people count garden birds on a single weekend, placed starlings fourth. They were once the most commonly recorded garden bird in Britain. Across the European Union, 40 million starlings have been lost since 1980. The cause is the industrialization of agriculture. Pesticides destroyed the larvae of crane flies, the primary food source for nestlings. Pasture declined, cattle moved indoors, and the grazing animals beside which starlings had foraged for millennia disappeared from fields. Old trees with natural hollows were felled. Buildings were repaired, sealing the gaps that generations of birds had used as nest sites. The global situation remains for now classified as least concern by the IUCN, with an estimated 150 million mature individuals worldwide, but the trend is descending, and the primary driver of population decline is low juvenile survival. Adult birds are not dying in unusual numbers. The chicks simply cannot find enough to eat. The paradox is plain. In North America, starlings are a catastrophe. In Europe, they are vanishing. In both cases, the determining factor is human behavior. And in both cases, the bird had no say. Did you see starlings this spring? Did they return to your garden, your balcony, your nest box, or was it quieter than usual? Write what you observed, because amateur observations are among the primary monitoring tools available to researchers. Each comment is a data point in a map that scientists cannot otherwise afford to complete. Now I want to return to the voice, because the story of the starling's vocal apparatus goes deeper than Mozart. The syrinx, the avian vocal organ, sits at the junction where the trachea divides into the 2 bronchi. In the starling, it is capable of producing sounds that include, under the right conditions, intelligible human speech, not with the clarity of a parrot, but in a form that people who keep starlings describe as recognizable. What is more significant than the output is the developmental process that produces it. A starling passes through the same stages of vocal acquisition as a human child: a listening phase, a sensory motor phase during which the young bird produces disorganized exploratory sound much as an infant babbles, and a crystallization phase during which the learned material stabilizes into a coherent repertoire. The difference is that in most songbirds, crystallization is permanent. In the starling, it is provisional. The repertoire never closes. The starling also refuted a long-standing assumption about avian olfaction. For decades, it was accepted that songbirds have essentially no functional sense of smell, their olfactory bulbs being small relative to those of mammals. The starling proved otherwise. Research showed that male starlings identify aromatic nest plants by scent, and that their olfactory sensitivity follows a seasonal rhythm, peaking in spring during nest construction and almost disappearing outside the breeding period. The sense of smell switches on and off on a schedule, a bird evaluating the chemical composition of yarrow and deciding whether to incorporate it. That is a level of sensory and cognitive sophistication that no one expected to find in an animal Linnaeus dismissed as common. Back to the flock, because I have not yet told you the most technically vertiginous part. In 1987, computer scientist Craig Reynolds created a simulation of virtual flocking agents he called boids, each following three rules: match the direction of neighbors, stay close, avoid collisions. Three rules produced eerily realistic flocking behavior on screen, but real starlings turned out to be more sophisticated than the model. When Cavagna and his colleagues analyzed their field data, they discovered that starlings respond to each other not on the basis of distance, but on the basis of topology, a fixed number of neighbors, regardless of spacing. This distinction is crucial. If starlings were using distance-based rules, the densely packed center of the flock would behave differently from the sparse outer edges. It does not, because every bird is tracking its 7 nearest individuals, regardless of how far those 7 happen to be. In 2014, the team measured the speed at which a turn initiated by one bird at the edge of the flock propagated through the full cloud. The transmission speed showed the signature of scale-free correlations. It did not diminish with flock size. William Bialik at Princeton in 2012 applied the statistical mechanics of condensed matter physics directly to starling flocks and confirmed that the flock behaves as if it exists at a critical point, the same mathematical regime as a crystal on the verge of transition, water at 0 degrees, a ferromagnet at the Curie temperature. At criticality, information propagates through a system without attenuation. This is not an analogy. The same equations apply. I will admit that when I understood what this meant, something shifted. We habitually treat physics and biology as different domains. Starlings demonstrate that the boundary is a convenience, not a fact. The statistics of murmurations compiled through a citizen science project published in 2017 in PLOS One by Goodfellow and colleagues at the University of Gloucestershire, drawing on more than 3,000 observations across 2 countries, show average flock size around 30,000 birds, average display duration 26 minutes. Predators detected in approximately 30% of events. Flocks range from several hundred individuals to 750,000. The recorded maximum in Denmark was 1.5 million. And all of this moves at up to 80 kilometers per hour. 80 kilometers per hour for a body weighing 75 grams, processing 7 simultaneous data streams, making directional corrections in milliseconds, transmitting those corrections instantaneously to every other member of a cloud that may contain 750,000 individuals. Describe that system to an engineer and ask them to replicate it within a 2-gram processor consuming a few calories per hour. No such device exists, but 150 million of them are flying over Europe tonight. In 2022, a team at the University of Technology Sydney published the Starling Murmuration Optimizer, an algorithm modeled on 3 identified flock strategies: splitting, where part of the flock detaches and explores a new region; diving, rapid exploratory movements toward candidate points; and wheeling, the compression and rotation of the group around a promising location. The SMO is designed to solve optimization problems where classical computation fails: engineering design, UAV route planning, management of large device networks, cybersecurity threat detection, real-time health monitoring. In benchmark tests, it outperformed numerous established approaches. A starling that does not know it exists became the prototype for artificial intelligence that runs infrastructure. This is the point that unsettles me. We extract the design principles from these birds and use them to build systems that manage the complexity of the modern world. We do this at the same time as we destroy the habitats that make the birds possible. We are copying the blueprints and incinerating the archive. There is a dimension of starling life almost never discussed in popular accounts: the roost. When murmurations end, the birds do not disperse gradually. They drop altogether. simultaneously. It looks from below as though the sky has collapsed. A million bodies plunge into reed beds, into tree canopies, onto building frameworks. In those reed beds, densities can reach 500 birds per cubic meter, 500 small warm bodies in the volume of a wardrobe. The temperature at the center of a roosting mass rises 5 to 8 degrees Celsius above ambient. For a small bird losing heat rapidly on a winter night, those degrees are the difference between surviving until morning and not. Research shows that birds in communal roosts reduce their metabolic rate by 15 to 20% compared to birds roosting alone. That energy saving is not achievable by any other means. But heat is not the primary function. Goodfellow's 2017 study showed that murmurations are first and foremost predator assessment events. When raptors were present in the area, flocks were larger, displays lasted longer, and at the end of the murmurations, all birds settled simultaneously in a single location. When no predators were detected, the same flocks split across multiple roost sites. The 26-minute aerial performance is, in functional terms, a collective security sweep. The birds rise, map the airspace, determine whether it is safe to commit to this location for the night, and only then descend. 26 minutes of physics-defying collective movement is the world's most elegant threat assessment protocol. The roost has costs. Reed, under the weight of hundreds of thousands of birds, breaks within days, so starlings rotate sites continuously, partly to confuse predators, partly because the previous site has been physically destroyed. The concentrated excrement of 500,000 birds acidifies soil, alters local vegetation, and can be smelled hundreds of meters away. For people living beside a major roost, the noise at dawn, when hundreds of thousands of birds simultaneously wake and begin communicating, is not gentle. In several cities in the UK and Italy, starling roosts have generated sustained civic conflict between residents and conservationists. But the roost also functions as a school. In the morning, as birds disperse toward feeding grounds, inexperienced individuals follow the older and more successful ones. Where experienced birds go, younger birds go too, without being told, without a signal, purely through observation. Knowledge transferred without language, navigation through social learning. The starling's brain weighs approximately 2 grams. 2 grams, but neuronal density in avian brain tissue is significantly higher than in mammalian tissue. Avian neurons are smaller, more compact, and more energetically efficient. Comparing gram for gram brain mass across classes is therefore a category error. 2 grams of starling brain is computationally closer to a small primate than to a rodent of similar body weight. That brain rebuilds itself twice per year. Vocal centers expand in spring when song matters and contract in autumn when it does not. New neurons form, new connections are established, old ones are pruned. There is no equivalent mechanism in human neurobiology. We do not seasonally reshape the functional architecture of our brains. The average lifespan of a wild starling is 5 years. The documented maximum is 22 years and 11 months. In 5 years, a starling will acquire dozens of sounds, raise a dozen or more offspring, fly 1,000 kilometers or more, and spend hundreds of hours as an element in a cloud of 100,000 bodies moving as a single entity. All of this in a body the size of a fist. The starling does not need your admiration. It has no use for your approval of its plumage. It will find a gap in a wall if you do not provide a nest box. It sang before dawn this morning, whether you were listening or not. What it does do is demonstrate repeatedly in its flesh and its feathers and its flight that simple rules applied consistently produce systems of astonishing complexity. That 7 neighbors replace 1,000,000 commanders. That a 2-gram brain solves problems that defeat supercomputers. That a blade of grass can be a pharmaceutical. That a song can be a life story. 5 sciences converge in the body of a creature that weighs as much as a chocolate bar. Physics, linguistics, neurobiology, ecology, and music, all simultaneously, in a bird that most people have never properly looked at. Linnaeus called it vulgaris, common. Mozart called it schön, beautiful. You have now heard the case for both. The final verdict belongs to you, and you can deliver it in the comments below. And if the hidden complexity of ordinary creatures is what you are here for, the next video has been waiting for exactly that.